Hello. Today we're going to look at simple harmonic motion. A particle undergoes simple harmonic motion if it oscillates about a midpoint, where its acceleration at any point is proportional to the displacement from the midpoint, and where that acceleration is directed towards the midpoint. A particle following a sine wave will undergo simple harmonic motion. Consider the sine wave y equals sine omega t. Omega is 2 pi f, and f is the frequency, which is the inverse of the period of the wave, that is, the time to complete one cycle. Acceleration is the rate of change of velocity with time, and velocity is the rate of change of distance with time. To find the acceleration of a particle travelling along a sine wave, we need to differentiate twice with respect to time. Y equals sine omega t. dy by dt is the velocity, and that equals omega cosine omega t. Differentiating a sine term gives a cosine term, but multiplied by the omega. Differentiating again gives d2y by dt squared, which is acceleration, and which equals minus omega squared sine omega t. Differentiating a cosine term gives us a minus sine term and multiplied by omega again. But sine omega t equals y, so the acceleration is minus omega squared times y. This tells us that the acceleration is directly proportional to the displacement y, but in the opposite direction. That is the condition for simple harmonic motion. The omega squared term enables us to calculate the frequency of the oscillations, since omega equals 2 pi f, and f is the frequency. What is happening? Consider one full cycle of a sine wave. As the displacement, x, increases, the acceleration increases, but in the opposite direction. At the point A, x is at a maximum, and the acceleration is also at a maximum, but the velocity is 0. At B, the displacement x is 0. The acceleration is 0, but the velocity is at its maximum and will carry the particle through to point C. But as it passes point B, the acceleration will change direction and will now push back to the midpoint. At point A, the particle has its maximum potential energy, but no kinetic energy. At point B, the particle has no potential energy, but maximum kinetic energy because it has maximum velocity. The combined total of potential energy and kinetic energy is a constant. As the particle travels along the sine wave, there is a transfer between kinetic and potential energy. The maximum amplitude for the wave we have considered so far is +1 and -1. In order to get other amplitudes, we need the formula y equals a sine omega t. A is the amplitude, and the amplitude of the wave will vary between +a and -a. We can calculate the velocity of the particle. From y equals a sine omega t, where a is the amplitude, we can deduce that the velocity is dy by dt, which equals a omega cosine omega t. We remember that sine squared omega t plus cosine squared omega t equals 1. Thus, cosine squared omega t equals 1 minus sine squared omega t. Therefore, cosine omega t equals the square root of 1 minus sine squared omega t, but sine squared omega t equals y squared over a squared, since y is a sine omega t. So dy by dt equals a omega times the square root of 1 minus y squared over a squared, and therefore dy by dt equals omega into the square root of a squared minus y squared. The velocity is at a maximum when y equals 0, that is, when there is no displacement. That is when dy by dt, the velocity, is omega a. Let us consider a spring with a mass m on the end. If the spring is initially at rest, and we displace the mass by a small amount and then release it, the spring will oscillate. The restoring force is given by Newton's second law, F equals ma. But Hooke's law also tells us that F equals minus kx, where k is the spring constant and x is the displacement from the mid position. Therefore, F equals ma, which equals minus kx. So A equals minus k over m times x. This tells us that the acceleration is proportional to the displacement, and that is simple harmonic motion. Omega squared is k over m. Therefore omega is the square root of k over m, and that equals 2 pi f. That enables you to determine the frequency of the oscillations. If the mass increases, then the frequency will decrease. Let us now consider a pendulum of length L with a mass m at the end. It is displaced by an angle theta. There is a tension T in the string and another tension T at the other end of the string. The physical displacement from the mid position is x. We can resolve the tension T into two components. The vertical component is T cosine theta. The horizontal component is T sine theta. It is the horizontal component which will provide the restoring force to take the pendulum back to its midpoint. Once again, Newton's second law tells us that F equals ma, which must equal minus T sine theta. Mg equals T cosine theta, but for small angles, Mg equals T, because for a small angle of, say, less than 5 degrees, cosine theta is almost 1. Strictly speaking, a pendulum will only oscillate with simple harmonic motion if it swings through only a small angle. Sine theta is x divided by L. Using Newton's second law again, F equals ma, which equals minus T, which is mg, times sine theta, which is x over L. This gives us A equals gx over L. The acceleration is proportional to the displacement, and that is simple harmonic motion. Omega squared is g over L. Omega is the square root of g over L, and from this you can determine the frequency of the pendulum's oscillations.